From Team 60 from Las Cruces, Wywick, and we're here to present our project, Maximize Lipid Output and Biomass Production of Algae in Open Pond Systems for Biofuel Synthesis.
Quite a mouthful.
Before we start, I would like to draw your attention to, we have a notebook here that has our code. I don't know if you guys saw in our final report, but it was paged weird, so this has it paged correctly, so if you guys want to take a look at it. And then I'd also like to draw your attention to our poster board behind over there. Okay, and I'll hand it off to Sophia for motivation.
All right, so the use of biofuels is really nothing new. The United States has been interested in them for a while, starting perhaps in the 70s when they instituted a 100% tax exemption for alcohol-based fuels. It's really no wonder why there's so much interest within the aspect of biofuels, just because they promise energy independence from our dependence on foreign oil and other fossil fuels. This is great for U.S. national security, so of course there's interest there. And additionally, as biofuel would be a domestic product, this would be good for the economy. Additionally, we live in an age in which environmentalism is becoming a growing policy concern. Therefore, as a carbon neutral fuel source, which emits no net extra carbon into the atmosphere, biofuels are even more lucrative. Additionally, biofuels, specifically algae biofuels, are extremely promising as perhaps the most promising biofuel for commercialization, given the fact that they're lipid-rich in comparison to other oil-leguminous crops such as corn. An acre of algae can produce 5,000 gallons of biofuel per year, as compared to corn's meager 420. This is extremely good just because we'll be able to put the prices down so that algae biofuel will potentially be able to compete with oil and natural gas and other fuel sources such as these. Additionally, as algae is not a food crop, there's no competition for algae, driving the prices even lower. And I'll hand it off to Ahmed.
All right, so before we could begin, we had to decide which type of algae that we had to use. We decided of Pseudochlorococcum sp, which is a green microalgae, and the reason why we used it is because it has a high lipid content. Now, algae biofuel is made when the finished batch from the system goes into a processing plant where the algae is extracted into lipids and biomass. The lipids are then smashed or use chemicals or anything to produce the actual fuel from the algae. And we used an open pond batch culturing, which is different from other systems, which I will explain later. Here are the production variables that basically dominate how much lipids you can have in the system. Carbon dioxide and light are used for the photosynthesis to basically have the algae grow. Water is basically the most important because without water, algae will not be there. Nutrient is also important because we can vary the amount of nutrients such as nitrogen in the batch. So then if we put too much or too little, it will change how much lipids that we have. So all of these relations they're all interrelated because if you increase too much nutrients, then you have to increase water and CO2, so then the algae can keep growing and grow and grow. So this is an open pond production system. There is just a little track where the algae is inside. There is a motorized paddle to keep the algae from sticking to the bottom and to make sure the algae on the bottom gets enough sunlight. There are 3 pipes leading in and out. There's algae in, which is if we need to start a new batch, then some algae will go in there and then it will continue to grow. Excuse me. Algae out is basically the harvest pipe. So when the batch is done, it will go out through there and then to the plant where it will be transformed into biofuel. The water and nutrient is basically, of course, explains itself. The water for the algae and nutrients to help it grow. So the current challenges are basically to compete with other non-renewable resources such as natural gas and oil. And also algae is much more expensive per gallon than gas at the gas station. So a problem here is to maximize the lipid and biomass content, so then we can have more biofuel per batch, and we need to make this more commercially viable so that there are algae farms basically everywhere where there is sunlight in the United States.
All right then, so now we go about quantifying all of these interrelationships so that we can adequately explore them within our model. We take our mathematical model based off of the math model developed by Aaron Tacker and his colleagues in their article, Growth in Neutral Lipid Synthesis in Green Microalgae. This allows us to quantify the amounts of lipids that we're able to produce within these production variables that Omen previously stated. These variable conditions that we subject the algae to within different performance scenarios can be modeled through the manipulation of input variables. This is important as prospective algae farmers can input the irradiance for their area to project, say, how much biofuel they'll be able to farm on their land and see whether or not their venture will be commercially viable. So the mathematical basis of this model consists of 4 state variables: the biomass concentration excluding neutral lipids, which is denoted by A of T, the neutral lipid concentration, denoted by N of T, the chlorophyll A content of the algae culture, denoted by H of T, and the extracellular nitrogen concentration. So the relationships between all of these variables are modeled through a system of 4 ordinary differential equations. All of these differential equations have, well, I'll go into that a bit later. But first of all, one challenge within the mathematical model was the evaluation of these ordinary differential equations. We initially looked for a nice general solution. However, that proved to be difficult given that we didn't have quite the machinery to find it. So we turned to numerical methods of evaluation, specifically the Euler methods. In addition to exploring the Euler methods, we explored Hume's method and Euler's midpoint method, and Euler's midpoint method is the one that's utilized within the model. We successfully implemented these numerical methods within our computational model, as Ian will later describe. So now to describe more of the relationships that really prompt our series of ordinary differential equations. So the model that we use is a bit of a conglomeration of various pre-existing biological models. For instance, the values for our biomass production are based on Droop's cell quota model, which states that growth is either nitrogen limited or light limited. This light limitation is accomplished using Liebig's law of the minimum. So it's saying that if there's not enough light, it won't grow, but by increasing light, we can increase growth. Additionally, with nitrogen limitation, we can model the fact that when there's a nitrogen stress, or the nitrogen dips below the minimum amount of nitrogen, we stop cell cycle progression and accumulate lipids, which is an important biological tendency that we can use and abuse in order to increase lipids. Additionally, we're able to account for variance in irradiance using the Lambert-Beer equations. This is important given that the algae will be growing at different levels within the algae pond, if you will. So the incident irradiance will be different at different levels. However, when we assume homogeneous mixing, as is exhibited due to the fact that the algae is mixed with the paddle, we can average the irradiance in order to get better numbers. Carbon fixation and photosynthesis itself, along with its various byproducts that are integral to the model, are modeled using Poisson's single-hit model of photosynthesis, which, as we all learned in biology class, is pretty basic. You have your inputs of irradiance, the photons excite the electrons, we produce ATP and fixed carbon, all that good stuff. So our simulation, our mathematical model demonstrated consistency with experimental data within Packer's article. There was a high correlation between the mathematical model and the experimental data, except at high nitrogen values. This could be possibly because there is an extra limiting factor on growth that was not accounted for. However, at reasonable values of nitrogen, our data is very consistent, which just goes to show that our data has good real-world applicability. I'll now hand it off to Ian.
Okay, so now we have, before we can start programming it, we need a programming language. So we picked Java. We picked Java because we needed the higher math functions. You couldn't get an agent-based language such as NetLogo or StarLogo. And then we also picked it because it was just the most common ground between members. Okay, so using the the object-orientedness of Java, we have this is kind of the basic layout of how our code works without the parallelization. The main object here is this algae growth model, and this is where we hold the state variables. It has the functions for the model and everything we need for the model. And then inside of this is 4 private classes that are implemented by derivative, or implements derivative, and those I'll discuss later. All those combined for the update call, and it sends us to this Euler's method that's just functions. And then we send this, if we're running for trying to do graphics, we have it encapsulated in this pond with graph data. And then this holds a thing, has an array of values for all time slots, so we could then graph the entire simulation. And then once it's there, we send it off to the grapher to graph it. Okay, so the algae growth model, as I said before, it holds the state variables, has the functions. The most important call in this is the update call, and this makes this call to the Euler's methods, and then like .hunes, and then gives you the state variable. As we said earlier, we actually use the Euler's midpoint. The 4 private classes in here have the state variables, implement derivative, and these are used to allow the Euler's methods to work. Okay, derivative. So, as I said, it was an interface to allow the Euler's methods to work. It does this by being able to modify the state variables and then get the derivative at different locations. And that's what it does. Euler's methods. This is just a set of functions that run the Euler's methods. This should only be instantiated once because it holds no data. It is just functions. Some basic pseudocode for it is you give it the step size, you give it the derivative equation, and then it moves it to the next time slot. Pond, this is an abstract object, so we have to extend a second object on top of that before we could instantiate it. And this implements runnable, which will be discussed later. And the basic run code for this is we tell it to run the model, update it for days to run, and then we divide that by step size. So if we have 10 days to run, a step size of 0.1, it will run for 100 times. Okay, so now to some of the parallel processing part. We need the parallel processing to be able to fully harvest the potential of modern computers by using multiple cores instead of running a single core. And we also wrote our own scheduler for it because to keep memory usage down. The basic idea of this is we add all of our simulations into a queue, and then we only have a certain set of simulations running. And then once it sees that one is done, it sends it to recorder, records only the data we actually need, and then gets rid of the rest of it. Okay, so simulation. This is an object that holds the pond that we need for running the simulation, the thread, and then the name of the simulation. This gives us a really nice basic API. We tell it to put the pond into it, tell it to start, and then we can just ask it, is it finished, and that's all we have to do with it. Simulation scheduler. This is where the rest of the program interfaces with the scheduler. It has this nice basic API of adding a simulation. We also can add just a string with only the data we need. We can do this to keep memory down so we don't have to have the whole simulation instantiated before we add it to the simulation. It'll instantiate once it is done with one of the other ones and is ready to start running. The simulation data handler, this is a protected class. The scheduler is in a package by itself. And it's protected to allow the rest of the program to not mess with the internals. That way we don't accidentally make mistakes with it. And it just holds a little bit of data to pass between the simulation scheduler, the queue, and then like the simulation, the runnable simulation, which I'll explain in just a second. Okay, so runnable scheduler. This is where we handle the starting and stopping of the simulations. It's in a thread by itself so that it can run while the rest of the code may not be running. It runs 8 simulations at a time. Why 8 is because the computer we ran on is a quad-core computer, and it's running 2 virtual cores on each core for a total of 8 virtual cores. So it maximizes our amount of computational power, but keeps memory usage at a minimum. It does rely on the Java garbage collector. Once we're done with the simulation, we just remove the pointer to it, and then the garbage collector will eventually get around to it, but we don't know exactly when it will really deallocate all the memory for it. So back to this graphic again. If you see this half of it is the simulation scheduler. We add it to a queue. Once it's done, it adds it into this array of simulations. We have that 8 simulations, and then done, it sends it to the recorder, records whatever data we need, and then that's how our parallel processing works. Right, optimization. So we optimize the initial values of biomass, neutral lipids, chlorophyll A, and then nitrogen content, and as well as the incident irradiance. So we ran 76,180 simulations to do our optimization, and the actual value we were trying to optimize was the amount that the algae grew from neutral lipids divided by how long it had been running for, so we could maximize the growth, not just how much we made, because if we got 100 days that it took and we got the most algae out of it, that's not as useful as if we got more in one day. And then we optimize each variable independently first, because to do it each individually, and then once we got those values, we use jointly optimize using values close to the ones we found optimizing independently. We did this because if we did the joint optimization to start with, it would have required about 1.12 quadrillion simulations, and we just couldn't handle that many simulations. So here's some of our results. As you can see, this is our first run of a simulation. We allowed a too large of biomass initial value. It degraded with that. It's modeled in the mathematical model that this can't happen, so we just force it to not be able to have quite that high of an initial value for biomass. So we optimize the initial value of biomass, the nitrogen, then the chlorophyll A, the neutral lipids, and then the incident irradiance. And once we had gotten these values that were pretty close to it, we did that optimization together and found this is our most optimized value for it.
Excuse me, how do I read that? Where is the what's the optimum there?
Okay, so the optimum is we've got the initial biomass is shown right here, and then the initial neutral lipids. So these are showing all the values that we found as the most optimized values, and then the piece over here is showing that this is our best growth of the neutral lipids grams per cubic meter per day. And as you can see, it is a very high number.
So I'm looking for a maximum in the last column.
Yeah, that's it.
Yeah.
Centralized.
That's the objective.
Yes.
Okay. And all these other. Okay.
Right.
But some of these columns don't change.
Okay, so why some of these columns didn't change is we were only optimizing one variable at a time until we did this final one. So we were optimizing only initial AFT for here, and then once we found this best optimum, we used that for the rest of the simulations until we did the final one. And then the same went for neutral lipids, that we picked a value that we thought was close to maybe what we wanted, and then optimized from there. And then the nitrogen as well. The nitrogen was actually interesting because we accidentally picked the right value to start with. I'm not exactly sure how that happened, but
We actually looked at a biological model that indicated that, so
yeah.
doing our research, I suppose.
Yeah. Okay, so this is a graph of the most optimized values. The actual optimization is only this very first part. This is over 10 days, but the best optimization was only for 12.24 hours to put it into, and then with a batch reset time of 4 hours to clean out the pond and then reset for the next time we can start growing the algae again. This green line here is the actual growth of it, showing, so that's the derivative of the equations. This orange line is the total biomass that is including the neutral lipids, and then this blue line is actually the neutral lipids, and then the red line is the biomass excluding neutral lipids. And as you can see, it very quickly dropped off, and starts having a very high neutral lipid content, which is good for our biofuel. And then I'll hand it off to Sophia for
Now
conclusion.
to explain some of these results. First of all, the batch time of 12 hours rather than simply leaving it in there for 10 days is because if we left it in there for 10 days, it would eventually reach a carrying capacity with the amount of space and nutrients that are available. Therefore, in order to maximize the amount of lipids that we're able to sustain over that period, we have to extract what we've grown and start another batch in order to stimulate new growth. Additionally, you can see this optimized value for the joint optimization. Right here, we have an optimized value of 5 grams per cubic meter of nitrogen, which is extremely low. This is not quite shocking just because there has been previous research to suggest that lipid production is increased during stress nitrogen conditions just because of a hold on the cell cycle. So that is explained. Additionally, we have an incident irradiance maximized value of 105 moles photons per meter square per day. This is extremely high as well, but the fact is that as per the mathematical model, increasing irradiance also causes an increase in biomass production and therefore lipid content. However, over 105, we saw a decrease in the amount of both growth and neutral lipid content. This could be due to the fact that photosynthesis system 2 is light sensitive. So when we have an incident irradiance over 105, we can start to induce photooxidative stress, which puts stress on the photosynthesis capacity itself, as per the Poisson model. Let's see. Additionally, I'd like to cover the fact that this has implications for the biofuel farmers themselves, as in order to reach this level of 105 moles photons per meter squared day, they could augment the photo period that they're using artificially through using artificial lights after dark or augmenting the photo period, augmenting the amount of light itself artificially. Additionally, here in New Mexico, we regularly get incident irradiance over 105 during some of our summer months, so that would imply that we need to have some shading on the algae so as not to induce that photooxidative stress. So overall, we've successfully created this computational model. It's been established as the mathematical model corresponds to experimental data, and this can have implications for algae farmers who are trying to realize whether or not their venture will be commercially viable. And additionally, it can be utilized to further explore the relationships present within the system. I'll now pass it on to Ahmed.
Okay, so our current optimization is just a mathematical optimization of just the growth. But this may not be so economically, the best optimization economically. So in the future, we plan to work on adding an economic computational model so that on top of our current growth model, so that we can maximize the economic value of the algae.
Basically, what it's going to do is figure out the cost necessary to sustain these optimizing conditions for neutral lipids, which may or may not be cost effective. We'd now like to call for any questions.
Wait, no, we have a demo first.
Yeah, all right, that.
Okay, so when I click the run button here, it's actually running the joint optimization really fast and then gives us this graph here. And as you've seen this graph before just a minute ago, and has, as you see, the growth, the total biomass, neutral lipids, and then biomass minus neutral lipids. Any questions?
I'm Cleve Moeller. I sent you some email yesterday. Have you-
Yes.
Ignore that email. All right?
All right.
I read things. I learned a lot from your presentation. Yesterday, I saw the printout of your code, and now I just saw it here, and it's very different.
Yeah.
And I was very disappointed in what I saw in the printout yesterday. And today, I see something very different.
Yeah, the pasting got it a bit.
I know, and yesterday it was unreadable, today it's gorgeous. So, and I've also talked to people about how you are learning to program in Java with all these little modules. And that's not my style, but it's your style and what you're learning. So, congratulations on that. And I apologize. Ignore my email from yesterday.
Will do.
And I'll send you some new email. It's my job to comment on your presentation, and I want to do it again based on what I've seen and learned today. So, much better job today. I've learned a lot about this today, so ignore the email from yesterday.
Okay.
Can you say something about what you learned from Packer and how you went kind of beyond that reference?
Okay. So when we were initially exploring the mathematical model, what we saw was that we had a model that will allow us to get both the neutral lipids and the growth. However, we really wanted to focus on neutral lipid production. And specifically, since we're in New Mexico and biofuels are being suggested as a potential venture here, we really wanted to explore the effects of irradiance since we have so much of this abundant sunshine. In order to go beyond the model, we had to factor in irradiance, which wasn't initially a part of the model. This is done using Leiber's law of the minimum. So what it does is basically we're saying that according to several of our references, the amount of irradiance necessary for growth is, there's a minimum amount of irradiance necessary for growth, and this corresponds to both the intensity of light and the photoperiod of light. And so we were able to look at another mathematical model in order to sort of add that in. Additionally, the implementation of the mathematical model was slightly different from the mathematical model implemented in Packer. Some of the variables exhibited in Packer were a bit vague, so we had to go a little deeper in order to figure out what exactly they meant and dig up the equations that actually represented them. Specifically, the value of Q sub 0 was a point of investigation. What we concluded was that as the little value of Q approaches Q sub 0, or the minimum nitrogen concentration approaches, the nitrogen concentration extracellular approaches the minimum, we find that we can increase growth. However, what this value of Q sub 0 really does is it allows us to integrate the point where we investigate the nitrogen stress, which is integral to our model. Is there anything else
Good,
you
no,
can
that's
verify?
good, thank you.
Okay.
I was interested in the part of your project that dealt with the scheduling of the runs.
Okay.
One of the questions I had was, did you have any intelligence in that scheduling to determine whether or not a run was worth continuing based on what optimums you'd seen so far, and maybe kicking the run out of the system because it would never reach the current optimum?
That is a very good idea. Our model did not have that in there. We just hadn't thought of that. So
Okay,
our run times were pretty short as they were, so we didn't have too much issue with that.
okay.
What grade are you in?
I'm a senior.
Junior?
Junior.
And how many years have you been in the challenge?
None.
This is my first year.
First.
We've got time for one more question. Sharon?
I was going to ask, with respect to the optimization, how did you choose the step sizes when you varied the parameters? So it looked like you stepped through very systematically. Was there any method in the way you chose those step sizes?
Okay, so the step sizes were just chosen as values that seemed to be small enough to be able to actually give us real results without getting to be so small. It's like we're not going to get here.
What we did was we looked at our Euler's method outputs and compared our outputs using values from the Packer article. The Packer article had graphs just like ours for the runs that they did with their default values, and so we were able to vary the step size of the Euler's midpoint method in order to approximate a curve that looks like the one that they had. Therefore, we verify that our model has results that are going to be consistent and experimentally verified.
How'd you find the Packard article?
Okay, so when we initially decided we wanted to optimize, we had to sort of figure out what exactly optimization meant. So we looked at various stages within the biofuel production cycle and decided to go right at the very beginning through lipids. So we looked for various articles that would model the growth dynamics of algae. We know what about we were looking for, and we found the Packer article. We had to get someone to get it for us because we didn't have the proper permissions, but
Just real quick.
This is
Okay.
it, last one.
All right, because we have some of the experimentation going on in terms of figuring out which algae to use in the ponds that they're talking about building down there between Deming and Mexico and all, have you had any validation of your predictions versus anything that they've done?
I'll take this one. No, we did not. Most of those are going to be not allowed outside because they are
Proprietary.
proprietary. So we didn't really check into that because we knew they would probably be proprietary.
however, we did look at the lipid content of pseudochlorococum, and it was one of the highest lipid contents of algae while being relatively hardy since we're in the COVID scenario.
Thank you very much.